So I'm going to go over how RAG embeddings work. And in this particular case, I'll be discussing how the string hello world is embedded inside of a Postgres database utilizing a vector. The standard, the 1536, so 1536 numbers, which are floating points inside of this vector. It is a standard from OpenAI. And, there are other standards as well. There's like 3072, which is much larger, right? You can get more precision out of the search. But the 1536 is standard for like a standard chatbot, right? If you have the 3072, you might, there are trade-offs where the size of your database is doubled and so on. But, there's a lot of stuff to know, and it's all very interesting stuff. But now, your typical database or your typical table in this particular database, you'll have your unique identifier, your UUID. You'll have your content, which is basically the original text kept verbatim, so it can be returned to the LLM, right? The LLM as context after retrieval. And you have your metadata, which is a JSON. It's useful for filtering or attribution, like source file, chunk index, timestamps, the author, etc., etc. And here is your vector. So you have a column or field in your database called embedding, and it's a vector. It's basically, it's mapping the string hello world, the characters, the text, to this particular to coordinates. I guess you can say coordinates, right? Based on all these floating points, these 1536 numbers that are here inside of this particular vector in a single row. I'm going to get into much more larger strings in a second. The schema in SQL is standard stuff, right? It's standard stuff. Create your table. Here we have documents. We have your UUID, you have your text, and you have your JSON field, and you have the embedding field, which is a vector, and the size of the vector. So you insert, right, into the table. You have your text, you have your JSON, and you have your vector. Now, the interesting thing, so in one sentence, here we get into chunks and tokens and all the other stuff that you might want to know about. When one sentence becomes many rows, right? So you're going to have many rows in your database, right? Many of these in your database, because you're going to have much larger context, much larger, more sentences, more paragraphs, and so on. So for a long package, a long passage gets chunked at token boundaries, right? Never mid-word, right? You never cut off never cut off a word, right, for a chunk. So that gets respected. Each chunk becomes its own row within its own 1536 dimension embedding. Notice the overlap. The last few tokens of a chunk reappear. They reappear at the start of the next one, right? Preserving context across the boundaries. So I'll get into that in a second. So let's say we have this larger paragraph. We have Satoshi Nakamoto published a Bitcoin white paper in 2008, proposing a peer-to-peer electronic cash system that would eliminate the need for trusted financial intermediaries. The protocol introduced, you see this is the next sentence, it's highlighted in a different color. The protocol introduced a proof-of-work consensus mechanism, allowing distributed nodes to agree on a single transaction history without a centralized authority. Again, next sentence, different highlighting. Mining rewards have approximately every 4 years, enforcing a fixed supply ceiling of 21 million coins and shaping Bitcoin's monetary policy through verifiable scarcity. So how do we do this now? Now we get to the first row. We have the first sentence. It gets put into context, and we embed it in the vector. So it gets its own set of coordinates. So all of this is embedded inside of this vector right here, right? Now we move on to the next one. If you'll notice that the ending of this ends with trusted financial intermediaries, right? So we have financial intermediaries. So the ending of the previous embedding is added to the beginning of the next embedding. Then we have the protocol introduced, the proof of work consensus, and so on, and it gets its own row, right? Its own record in the database with its own embedding. And then once again, you see we go to the third paragraph, and this again has the ending of the previous embedding, right? Any centralized authority, centralized authority. Minor rewards have approximately every 4 years, and so on. It gets its own embedding. So yeah, interesting stuff. And like since I've learning about this and how everything is done, it's like it's really interesting. But so we have the thing. So why chunk, right? This is a question, right? The Shakespeare always pondered, right? So why chunk? So a single embedding for the whole passage would average out the meaning, right? A single embedding for the whole passage would average out the meaning, right? So you're honed in on the meaning of that particular sentence in that embedding, right? So 3 focused chunks give the precise targets. A query about the halvings hits chunk 3, not the noise of the whole package. So that's why you separate it into chunks. It makes sense if you want precision. Now, token boundaries. The chunk splits at each token boundary, never mid-word, right? So it's not going to take it's not going to take the word rewards and say REW is one token, and then WARDS is another token, and then move it into another embedding and so on. So the boundaries are respected. So intermediaries stays whole. Each chunk lands within the configured token budget. Here, around 30 tokens, right, in production, so 500 to 1,000 tokens. So this is just a really small example, but obviously context is a little bit larger when you're in the real world with a real application. So 500 tokens, 1,000 tokens, and so on. Right, here we have 30 tokens as a rough example to give you the concept. Now the overlap, each chunk begins with the tail of the previous one, right? I've discussed this already. It preserves context across boundaries, so a query about proof of work doesn't mix with its antecedent, I love that word, reference to the protocol. And 3 vectors, not 1, of course, right? 3 vectors, not 1, because you have 3 different embeddings, the same passage, 3 different rows, 3 independent 1,536 dimension embeddings. At query time, similarity search ranks all chunks across all documents. The best match wins, regardless of the source. So there you have it. For a beginner, this might be a lot to take in, and I guess once you get the swing of things and once you get the hang of it, it just becomes like normal, I guess. Because once you start focusing on how things work, it's pretty cool. So do me a solid and hit that like button and hit that subscribe button if you want more content like this.